Hello, my name is Catherine Amstutz, and this is Physics Lab 3. The purpose of this lab is to analyze the motion of a star around a black hole and to determine the mass of the black hole. The mass of the black hole was 8.08129 times 10 to the 33rd kilograms. The second part was to determine the initial velocity a ship leaving a planet must have to avoid the black hole. The initial velocity that I found was negative 2 times 10 to the 6th for the x component and 1 times 10 to the 7th for the y component. Some fundamental physics principles necessary to understand this lab are Newton's law of universal gravitation, which is that the force of attraction between two objects is going to be the gravitational constant, 6.7 times 10 to the negative 11, times the mass of each of the objects, divided by r squared, which I'll get back to, times negative r hat. So r is the position vector. It's essentially the position vector of the system as position vector of the source. R hat is the unit vector of that, and then the r is the magnitude of that vector squared. Newton's second law is also important. It's used to derive the velocity and position update formulas, which will be especially useful in part 2 of this experiment. And then this experiment also touches on parallel and perpendicular components of net force, where the parallel component is going the same direction as the motion of the object, and the perpendicular component is going orthogonal to the motion of that object. The models that are used in this experiment are both computational and use WebView Python. For part 1, the system is the black hole, the surroundings the star, and the initial conditions are the mass of the star and the change in time. While for part 2, the system is the ship, the surroundings are the planet and the black hole, and the initial conditions are the masses of all the objects involved. For the code, the mass of the star and delta t are given the problem statement. I just converted delta t from 1 day into seconds. And then I created a total mass counter and just a mass counter that's just essentially counting the number of times you go through the calculation loop, so I could find the average mass. Then I used the definition of momentum to find the initial and final momentum, and to find delta V and delta P from the given information. Then because net force is equal to change in momentum over change in time, we can calculate that. And we can also calculate the parallel component of the net force from this equation here, where the parallel component of momentum is going to be equal to that parallel component. And then because the parallel and the perpendicular components together give you the net force, you can also find the perpendicular component from this. I then rearranged the law of universal gravitation to find the mass of the black hole, as is shown here. And then mass is going to be a little bit different every time. So again, I am adding up the total mass here and have a mass counter so that I can find the average at the end. And then this is what the model looks like when it is actually running. You can see the slightly different masses, but they're all quite similar. They're all 10 to the 33rd, and they all work together to get the finalized mass of 8.08129 times 10 to the 33rd power. And that is part of the initial components for part 2. Part 2 essentially uses the universal law of gravitation a lot to find the net force on the planet and then the net force on the ship. It also uses Newton's second law to find the final position and velocity, essentially the new position and velocity of the planet and the ship every time you go through that loop. And then once I wrote that, I could start plugging in initial x and y components of velocity to actually start verifying what would work. And this is the result of what you saw on the previous slide, that initial x and y components of velocity. You can see the planet staying in its orbit, and our ship has escaped the black hole. So in terms of comparing data and model predictions, we can't do this because we don't have any actual data, just computational models. Some potential sources of error in our models is all theoretical, but we are still making some approximations. We are rounding g to 6.7 times 10 to the negative 11th. We're approximating with v final for v average in the position update formula, and these little tiny differences are going to increase every time we iterate and have a little bit of propagation of error. So, what if we wanted to orbit around the black hole? Well, we would not have as great of an initial velocity. So I decreased the absolute value of the x and y component and then did guess and check from there. And I found that one of the numbers that would work is the x component of negative 9 times 10 to the 5th and a y component of 9 times 10 to the 6th. And this is the result of that. So what does it mean? how does the net force and its parallel and perpendicular components differ from the change in momentum? So first of all, the net force is equal to change in momentum over time. Net force parallel is equal to change in momentum parallel over time as well. But forces parallel or anti-parallel to the direction of motion impact the magnitude of the momentum, while forces perpendicular to the direction of motion change the direction of the momentum. In this experiment, we used computational modeling to determine the mass of the black hole, the initial velocity necessary to escape the black hole, and the initial velocity necessary to orbit the black hole.